Hello everyone, welcome back to this online class. Today I want us to look at how to find the integral surface of the symmetric equation given by dx over x squared minus yz is equals to dy over y squared minus xz is equals to dz over z squared minus xy. So to be able to solve this equation, we need to find two unique solutions, which we are calling the integral curve. So the first solution, remember there are quite a number of techniques of finding such solutions, and the best way is through trial and error method. So let's see how to find the first solution of this differential equation. So we are going to write this one. If I take dx minus dy, you must do the same in the denominator. We'll have x squared minus yz, then subtract y squared minus y squared minus xz. Equate this to dy minus dz. Everything over, do the same in the denominator, y squared minus xz. We are subtracting z squared minus xy. So let us simplify those denominators. We simplify the denominator. Let's start with the left-hand side. I want us to take note on the left-hand side. Take note that x squared minus yz minus y squared minus xz, this is the same as x squared minus y squared, I'm opening the bracket, then minus yz, then plus xz, which you can as well write as x squared minus y squared. Let this be one group. In the other group, I can see z is common, so we'll have plus z into x minus y, which you can as well write as, you see, x squared minus y squared is the same as difference of two squares. So we have x plus y times x minus y, then plus z into x minus y. And you see x minus y is common. You can factor that out, x minus y outside. Then we remain now with x plus y plus z. That is the denominator on the left-hand side. What about the right-hand side? What are we going to get? And similarly, you can write y squared minus xz. We are subtracting z squared minus xy. Now, what will this give us? It will give us y squared minus z squared, then minus xz plus xy. If you open the bracket. So the next thing is to now factorize. Before factorize, let me group as. I can write this in the next line. Let me rub this so that I go to the next line. So this we can as well write as y squared minus z squared. That is one group. Then in the other group, I can see x is common, so x outside into y minus z. But y squared minus z squared is the same as difference of two squares, which you can write as y plus z times y minus z. Minus, then this plus x into y minus z. Y minus z is common, so factor that out, y minus z outside. What we remain with is x plus y plus z. So we go back to our equation in case 1. Let us now substitute. So therefore, we can now say therefore, let me pick a different color. We can now say therefore dx minus dy, the denominator now after factorizing, we get x minus y times x plus y plus z. This is equals to dy minus dz over y minus z times x plus y plus z. So that is after factorizing. Now you see x plus y plus z will cancel with the other x plus y plus z. So this thing can now be written as dx minus dy over x minus y is equals to dy minus dz over y minus z. So now it is easy to integrate. So let me introduce integrals on both sides. Integrate this, also integrate this. For you to integrate the left and the right hand side, use substitution. So on the left hand side, I'm just explaining how to get that integral. Take note that if on the left I let u to be equal to x minus y, then it means that the u will be equal to the derivative of x minus y, which you can write as dx minus dy. What about the right hand side? The right hand side, I'm going to say let v be equal to y minus z. So I need to know what is dv. So dv is the same as derivative of y minus z, which you can write as derivative of y minus derivative of z. So therefore, this integral can now be written as the integral of du over u, and the other one is the integral of dv over v. So you know how to integrate, which you can also write as, let me write this in a better way. You can also write this as the integral of 1 over u du is equals to the integral of 1 over v dv. So when you integrate, you're going to get natural log of u equals to natural log of v plus natural log of a constant c1. Make c1 the subject. So from here, it is clear that or u over v, you are applying the laws of logarithms, that should give you c1. But what was u? Our u was x minus y. Our v was y minus z. This is equals to c1. So this one is the first integral curve. Let me bracket this. This is the first solution. Remember, we need two unique solutions. So we have found the first one. Let's see, is there another way of finding another solution different from the one that we have found? So this solution is called an integral curve, and we need two of them. So go back to our equation. Are we able to find another solution different from the one that we have found in case 1? Yes. You can use the method of multipliers. Remember how that method works is that you need to choose values of L, M, and N such that if I take L times P capital, remember the general form is dx over P equals to dy over Q equals to dz over r. So I need the values of L times P. I need to know L plus times P added to M times Q added to N times R. What values of those constant L, M, and N, when I multiply by P, Q, and R respectively and add them, I am going to get 0 on the right hand side. If that is the case, then that will imply that L dx plus M dy plus N dz must also be equal to 0. So when solving such kind of equations, there is no formula. It is just a matter of trial and error, what we call intuition. Just look at the equation and then see what will work for you. So if I look at the equation, I can use the method of multipliers where L is y plus z, M is x plus z, and N is equals to x plus y. So when you have those multipliers, it's a bracket. If you multiply, because this is our P capital, the whole of that denominator of dx, the denominator of dy is our Q capital, and that of dz denominator is our R capital. You realize that when you multiply, you're going to get 0 on the right hand side. So having explained how to find those multipliers, that will lead us to case 2. So we write case 2. Using the multipliers, so we have said here our L is y plus z, our M is equals to x plus z, and our N is equals to x plus y. Let me see whether I'm going to get 0. So LP plus MQ plus NR, what will it give us? It will give us y plus z times x squared minus yz, that's our P, plus our M is x plus z. We are multiplying this by y squared minus xz, which is our Q, minus xz is our Q, then plus our N, which is x plus y. We are multiplying this by z squared minus x, y. Let me open the bracket. When I multiply by y, I'm going to get yx squared minus y squared z plus x squared z minus y z squared. I've opened the bracket in the first term. The second term, if you open the bracket, you're going to get xy squared minus x squared z, then plus y squared z minus x z squared. That's the second term. When you open it, then the third term, open the bracket in the third term, we are going to get this. It will be plus x z squared minus x squared y plus yz squared minus x y squared. Let's see, are we going to get 0? X squared y, do we have another negative x squared y? You check this one, they'll cancel. I can also see negative y squared z. Do we have positive y squared z? Yes. Positive y squared z, I can see it. This one, they'll cancel. we also have, let me use a different color. Can use green. X squared z, do we have negative x squared z? Yes. Another color, just to distinguish how those things are cancelling out. Negative yz squared, do we have positive yz squared? Yes, this one, this will cancel out. We still remain with some terms. Let me pick another color. Xy squared, do we have negative xy squared? Yes, this one. And lastly, I can pick now yellow. We have xz squared, and that's negative. The positive xz squared got to cancel. So you realize that having cancelled those terms, we now remain with the result 0. So I told you these multipliers are chosen just by trial and error. Just choose them arbitrarily. What values of L, M, and N, such that when you multiply by P, Q, and R respectively, and then you add the result, you're going to get a 0. So because this is true, it means that therefore, even L dx plus M dy plus N dz must also be equal to 0. If I substitute the values of L, M, and N, you're going to get y plus z dx plus x plus z dy plus x plus y dz. That should give us 0. If you open the bracket, you're going to get this, or y dx plus z dx, you can see plus x dy plus z dy plus x dz, then plus y dz. That will give us 0. Then I now regroup them. The first group will be this, y dx, and I can see this x dy somewhere. That will form one group. Y dx plus x dy, one group. Another group is z dx, and I can see that should not be cancelled. Just underlining z dx. I can see this x dz, so I'm going to add z dx plus x dz. And the last group is z dy and y dz. So plus z dy, then plus, excuse me, y dz. That should give us 0. So look at this one. The first term is the same as derivative of x times y. That is from product rule. When you keep y constant, differentiate x, then now keep x constant, differentiate y. Now plus, this other term is the same as derivative of x times z. Again, keep z constant, differentiate x, that is z dx, plus now keep x constant, differentiate z, that is x dz. And finally, the third term is derivative of y z, and that should give us 0 on the right hand side. So we now integrate directly. Integral So remember, integral and derivative are inverses of each other. So they'll cancel. Integral and derivative, those are inverses of each other. So they cancel even here, even here. And when you integrate 0, you get a constant. So what we have after integrating, we'll have xy plus xz plus yz. That should give us a constant of integration. C2, when you integrate 0, you get a constant. Why? Because you see, when you differentiate a constant, you get 0. And we said integration is the reverse of differentiation. So what you have found here is the second integral curve. We have managed to find the two unique solutions of the given differential equation. Now, once you have your two integral curves, how do you find the integral surface? This is how to find the integral surface. So you can say, therefore, integral surface we are going to call it a function phi, an arbitrary function. Let's use the small phi. Phi of C1, C2 should be equal to 0. If I replace C1, C2, we'll write this, or our C1 we got x minus y over y minus z, and our C2 we have found xy plus xz plus yz. That should give us 0. The phi here is an arbitrary function. This thing can also be written as, you can write, or you can decide to factor out any of those parameters. I could factor out the first parameter so that I have x minus y over y minus z is equals to, let's call it phi 1 of xy plus xz plus yz. That's another way of writing our integral surface, which I'm calling star. That's another way of writing it when you decide to factor out one parameter. I have factored out the first parameter, or somebody could factor out the second parameter. So this thing can also be written as xy plus xz plus yz is equals to phi 2. It's just an arbitrary function. Phi 2 of x minus y over y minus z, etc. So phi 1, phi 2, those are arbitrary functions. Even if you leave your answer as equation star, there's no need of having to factor out some parameters. Those three answers are the same thing. So thank you all for watching. Please subscribe to my YouTube channel. That is Professor Francis Okech. Just go to the YouTube search and then type Professor Francis Okech. Also, don't forget to like, share, and comment on this video. When we meet next time, we're going to look at other problems in partial differential equations. Bye-bye.